Right, okay, so Vasco and I have been writing a book on session types for some time. So the title is What We Have Learned, but I mean, I've prepared the slides, so it's sort of my view on it. It may be that Vasco would have a different view. You'd have to ask him. I did send him the slides at lunchtime, and he said he thought they were good, so let's see. Now, I should say this is not exactly the first book about session types, because there's Ornella's thesis, which was published as a book and is mostly about session types. But I think this is the first, setting out to write a book which is an introduction to session types. So in the beginning, which I don't exactly remember when it was, but I think we were in London at an event. Let's write a book about session types. Yes, good idea. And this was in either 2014 or 2015, so quite a long time ago. And then nothing happened. So in the summer of 2019, we again said, let's write a book about session types. Yes, good idea. And at that point, we actually took the next step and submitted a proposal to Cambridge University Press. The proposal was reviewed, accepted. We had a contract. Some deadlines were suggested. And so we got started. So in the autumn and through to the beginning of 2019, 2020, I had a few visits to Lisbon, and we got started. 1st of March 2020, Vasco arrived in Glasgow to spend part of his sabbatical on a 3-month visit in Glasgow. And you know what happened next. So 18th of March 2020, Vasco went back to Lisbon. And I'm sure we've all got similar stories. So, I mean, Luca Padovani was also supposed to visit Glasgow for several months that year, and he never even got as far as arriving, and so on and so on. So we carried on in remote mode, and we've been collaborating for a long time with a lot of remote working. So that was not too bad. So we thought, well, how hard can it be to write this book? We know what we want to include. We've got a lot of source material, so there's this paper by Vasco, Fundamentals of Session Types, which is a nice presentation of all the basics. We wanted to include subtyping, so there's my paper with Malcolm Hole about subtyping. We wanted to include functional programming, so Vasco and I wrote a paper some years ago about functional programming with session types. And I now realise when putting these slides together that the title of this paper doesn't say anything about functional programming, although it's published in the Journal of Functional Programming, so maybe that's enough to say that it's about functional programming. We wanted to include something about the encoding by Nava, Giacchino and Sangiorgi about, this is what was referred to in Jorge's talk actually, encoding session types into linear types. We wanted to include something about the developments of the propositions as types connection, the work by Luis Caires, Frank Fenning, and afterwards by Phil Wadler. And we decided at an early stage that we were not going to include multi-party session types, because just dealing with the main topics in binary session types is plenty. It certainly would be a good idea for someone to write a book about multi-party session types, but I don't think it's going to be me and Vasco. So how hard can it be? Well, so of course you have to work out how to present everything step by step in a consistent way. We wanted to give a good account of the sort of the theory of the co-inductive approach to dealing with infinite session types. You can find a lot of papers that say, well, we'll interpret these rules co-inductively, but to find a thorough explanation of what that really means, we wanted to do that. How to deal with infinite process behavior, so replication or recursive definitions or whatever. How to deal with the, so at the core of session types, you've got linear types without sharing, but then you want to add nonlinear types with sharing. There are different ways of presenting this. Sometimes your type environment has 2 regions, some of which are shareable and some of which are not, or you can have explicit contraction and weakening rules, as you would see in a logical system. I said we wanted to include the propositions as sessions material, the linear logic correspondence, but there are these two rather different presentations of that, the original one by Keyes and Fenning, and then the later one by Wadler, so that there was a decision to be made there. And I said that some deadlines were suggested. So we originally suggested a very optimistic deadline, and I can't remember exactly what it was. It might have been sometime towards the end of 2020. And at some point we realised we weren't going to make that deadline. So I contacted our editor at CUP and said, look, I think it's going to take a bit longer. And the way he responded, it sounded as if he was surprised that we were taking the deadline seriously at all. He was quite surprised that we were bothering to inform him that we might not satisfy the deadline. Anyway, so we got to work and we started simple. So we start with a very, very simple system, no recursive types, no recursive process behavior. Everything we do throughout uses this double binder style, so separate names for the two endpoints of a channel, and new binds both of them. You can find different treatments of the end session type in the literature. Sometimes there's just one end type, sometimes it's separated into two dual types. Sometimes end is a sharable type, sometimes it isn't. And we started off with no copying or sharing at all, so it's purely linear. So it's quite a basic system. Something we discussed quite a lot is that we don't have any primitive data types, so it's just session types. And then we encode Boolean types using branching and selection, and then use some examples based on Booleans. And the plus point about this is that it keeps the language as simple as possible, because if you start introducing primitive data types, if you say you want to have integers or whatever in your examples, I mean, either you have to actually properly develop the typing rules and theory for that, or you have to be informal and say, well, we could easily add primitive data types and then we'll use them in this example. But then if we say we could easily do X without actually showing how to do it, then the book isn't fulfilling its need to provide a foundation. So this is what we ended up doing. And the main drawback from my point of view is that there are an awful lot of examples where you're passing around channels of type end just because you want to have some kind of piece of data to pass around. Anyway, that's what we did, and then we prove type preservation and type safety. And the structure of the first chapters is that we start with this simple approach, and then we gradually extend the language and sort of go through a similar development, showing what's different. So one thing, of course, we've heard already today, another key property of session type systems is session fidelity, which is that the sequence of messages that's actually exchanged at runtime matches the specification expressed in the type. And a lot of multi-party session type papers prove session fidelity, but we didn't manage to find a paper that proves session fidelity for a binary session type system. If anyone knows one, please let us know, because it would be good to have a citation. And there's actually, as you know, if you've tried it in the multi-party setting, it's you need some extra machinery to prove session fidelity. So I think in the end, this has turned into a rather complicated exercise for the readers. But it would be nice to have a citation for where someone else has done it. So then we move on to infinite behavior. As I said, we start off by infinite type as actual infinite objects with infinite derivations. We try to explain the foundations for this. This paper by Dexter Cozen and Alexandra Silva, Practical Co-induction, is a very good reference for doing things co-inductively. Then we move on to do the usual kind of finite syntax using a rec construct. We thought about trying to take the same approach with infinite process behavior, and it seemed to get a bit complicated because of dealing with variable binding in a thorough way. We're not quite sure how to handle an actual infinite typing derivation for an infinite process where you've got an infinite sequence of bound variables. So we just went straight to a finite syntax using systems of mutually recursive equations defining process behavior. Something else that came up this morning in Peter's talk was this point about having to be very careful with the definition of duality of session types if you have recursive types that are not tail recursive, so if you allow recursion in the message position. And so we've included an explanation of how that works based on the approach of Bernardi and Hennessy. So then we move on to nonlinear types and sharing. And the key thing here is that if you've got session types which are stateless, so as for example here a recursive type where after sending the first message you go back to the original type, then these types can be safely, channels of these types can be safely shared. You don't get race conditions due to the statefulness. Now, some presentations of session types, start off with pre-types, and then you add a qualifier which is either lin for linear or un for unrestricted. So unrestricted means shareable, and then you have to be a bit careful that if you're constructing a type and declaring it to be un, you have to make sure that the structure of the type was actually safe to be declared as un. So in the end, we've got a different approach, which is that instead of lin and un being qualifiers that you attach syntactically to types, they're predicates that a type can satisfy. So the types that satisfy the un predicate are exactly the ones that have this stateless character. And the types that don't satisfy the un predicate satisfy the lin predicate, so they're negations of each other. And one thing this supports, which actually was already in Vasco's paper on fundamentals of session types, is that it's possible to have a type which starts out as linear and then evolves to become something shareable. So you can have a channel which initially must have only one owner to avoid race conditions, and then after some initial sequence of communications that the channel can be shared. So this is a little example here. An initial input of a Boolean and then going into a stateless type that repeatedly inputs ints. And there you see I've violated the principle of not having any primitive data types, but you see how attractive it is to be able to just throw in bool and int when you're trying to explain something. So the way we deal with the shareable types is that we have explicit rules for weakening and contraction. So this is contraction. So contraction means replacing two names y and z by a single name x and doing the substitution. And you can only do this if the type T is unlimited or shareable. We had quite some discussion about the concept of sending a channel on itself, so where the message is the same as the channel, and it's possible to construct examples of processes that do this. They often seem a little bit artificial. Now, the thing is that once you've committed to having an explicit contraction rule like this, then you can automatically type processes like this. There's no choice about it. So you're stuck with them in the situation where the type is unrestricted. So then there's a separate discussion you can have about whether it's possible to do send x on x when the type of the channel is linear. And it is possible to make sense of that if you decide to insert a typing rule for it, and then then the difficulty is in terms of writing the book, when you've got design decisions like that, and you set them both out, and then what do you do in all the subsequent chapters? Do you maintain this, these two options, and so on? So this is one of the ways in which things get complicated.
What is your decision? You include it or this XX?
So it goes. We include it for a while and then stop. So the next chapter. so after the sharing chapter, the next chapter is about subtyping, and we still have this send on self possibility. And then eventually we get to a chapter about type checking algorithms, and then we just drop the linear one because it's a bit complicated. but you still have to, for the shareable types, you still have to allow x send x because it's there. So we have a chapter on subtyping. This was one of the chapters that really didn't have a lot of problems. We did manage to closely follow my paper on subtyping. We did make a small discovery. I'm not sure whether this is original or not, but I don't think I had seen it before. So a lot of work that has linear types and also subtyping, just, from the point of view of subtyping, the linear world and the non-linear world are just completely separate. So if you've got a subtyping relationship, either the types are both linear or they're both non-linear. Now actually, in the paper that Vasco and I wrote about functional programming with session types, we have a subtyping relationship between linear and non-linear function types, which is quite convenient in some ways, and that's safe. But still, the linear and non-linear session types were separate. But once you've got this idea of lin and un just as predicates that a type may satisfy rather than decisions or rather than syntax, it turns out, the subtyping relation is also defined on the structure. So it turns out to be possible to have a subtyping relationship between session types where one of them is linear and one is non-linear. So here's an example. So this is an example using an internal choice type. So we've just got one option, which is A, and then the continuation is the same as the original type. So this is stateless. It's shareable. It satisfies the predicate. This one starts off with a choice with two options and then goes into that one. So this has to be linear because you've got this first step which is not stateless. But according to the definition of subtyping, L is a subtype of U, so you get this mixing between the worlds. And this looked a bit, when we noticed this, we thought this was a terrible mistake and something must be badly wrong and we'd be back to the beginning for this chapter and so on. But it turns out that it's perfectly safe. You would worry intuitively that you might have a channel which is supposed to be uniquely owned because its type is linear, and then you use subtyping to promote it into a situation where it's not uniquely owned anymore, it's shared, and surely something could go wrong. But actually what happens is, if we take something of type L, promote it to type U and put it in a context where it's being used with type U, well, the context in which it's being used can only be using it in a stateless way, because that's what the type U says. And so you don't get the opportunity to take advantage of the stateful nature of L, and so nothing can ever go wrong. So the promotion in this case, usually going up the subtyping relation, you're discarding some information, you're forgetting something, and what you're forgetting here is that the L type had this stateful character. So everything's fine, but that was quite an interesting observation. So we are, I'm afraid, still working on a chapter about algorithmic type checking, attempting to follow the approach taken by David Walker in his chapter on substructural type systems in Advanced Topics on Types and Programming Languages. And what we're doing is, all the type systems in the book, of course, are presented by a collection of inference rules, and so the type checking algorithm is also presented as a collection of inference rules. This is quite common in the literature. It makes everything look consistent with the way that we present the declarative type systems. But you could argue that if you want to present an algorithm, doing it by a collection of inference rules is actually quite strange. And if you look at papers that are actually about algorithms and see their presentation of an algorithm, what you definitely won't see is a collection of inference rules. You'll see some pseudocode that you can actually see how it maps into code. So this then leads into questions about how should we present these rules? Should they be as clear as possible? Should they be as compact as possible? Should they make the proofs as easy as possible? Should these rules make it easy to see how to do the implementation? And this has led to a lot of discussion. Functional programming. Thankfully, this chapter did proceed without any difficulties, and we managed to base it on our previous work, so that's all okay. Encoding session types in linear types. So this is the work by Ornella and the others. We did something which you might say is cheating a little bit, possibly, but one of the things that this encoding has to deal with is that the source language is this double binder form of session pi calculus, and the target language is pi calculus with a linear type system, but not with the double binders, so just a single mux. And this leads to a certain amount of extra, bureaucracy and bookkeeping in the definitions and proofs and so on. So we decided to simplify our lives a little bit by converting the linear pi calculus, the target language, also into a double binder language, which is then consistent with everything previously in the book. We did a little bit of experimenting about exactly how to define this encoding. So, the original work, this encoding is defined on untyped processes, and some later work defines it on typing judgments, and it's a question of how you make the proofs go through. So we've ended up with a small variation where what we're translating is untyped session pi processes, but they do have type annotations on their restrictions, and we have optional type annotations on the restrictions in the target language, and this enables us to define the encoding without having to assume a typing context, but all the proofs seem to work quite well. And then the final chapter is about the linear logic connections and the propositions as types approach. We discussed this quite a lot. In the end, we decided to follow Wadler's approach, the CP approach, rather than the original approach by Frank and Luis using the dual intuitionistic linear logic. I will say that we now have a much better understanding of the differences between these two presentations. And I think one aspect of this is that the DIL approach matches the normal pi calculus treatment of replication quite well, in the sense of sort of pulling out one copy when you need it from a replication, whereas the Wadler CP approach, you sort of duplicate an entire replicable process and then convert one of them into a single form that you want. However, we felt that the Wadler CP approach matched quite well the general style of typing rules that we had earlier in the book, including the explicit contraction and weakening rules. So we decided to go with that. So the title of this slide is duality, which is of course essential in session types, but on this slide it's not what you think. So this is going a little bit off track, but when I was much younger, growing up as a child, I remember that my sister had a big poster which illustrated lots of common sayings and proverbs, and a lot of them were in kind of dual or complementary pairs, which was quite an entertaining way to present them. So one of these is, many hands make light work, or there's the more intellectual version, which is that two heads are better than one. But the dual of that is that too many cooks spoil the broth. And of course we know about that in the context of software engineering. So I don't think we've spoiled the broth or the book. I don't think two cooks is too many. I think it's a helpful number. I think we've worked very well together. Another well-known saying is that a problem shared is a problem halved. I think this is perhaps more often applied to emotional problems rather than technical problems. But my variation on this is that a problem shared is a problem with two solutions that then have to be discussed and compared at length. But I think normally you end up with something better because it's been compared and discussed. So we do think we've nearly finished. Thank you to everyone who is going to read chapters and give us feedback. You don't know who you are yet. If you're thinking maybe they'll ask me to read a chapter, yes, we will. Hopefully quite soon. We hope the book will be a useful introduction to binary session types and a reference. Working together has been more fun than trying to write a book solo. It's certainly going to be a better book than it would have been if I had tried to write one myself. You'd have to ask Vasco whether he thinks the same. Someone should write a book about multi-party session types. I also think it would be very interesting to have a book that took the propositions as types approach right from the beginning and did everything in that style. It would be, I don't know if any of the obvious people have thought about that, but it would be a good thing to do. So that's it. Thank you for indulging me by listening to a talk about what Vasco and I have been working on, and we hope you'll hear more about the availability of the book before too much longer.
Not a question, but the comment is that X send X, this you can encode the untyped lambda calculus. It's like lambda x dot xx and lambda x dot xx. So you can encode, if you can send channel to channel, you can encode untyped lambda calculus. That is one example, but I thought your subtyping algorithm doesn't have any problem to send channel to send, I think. But it may be shared channel. I don't know.
I don't think it's a problem. I mean, you need a suitable recursive type for the channel,
Yes.
and then I think
Of course.
everything's fine. Yeah.
But you can, that is also useful for encoding.
Right.
Just,
yes, I see what you mean. Yes.
Another question on the back.
Okay, so a technical question and a challenge. So you
can put it.
is it on? Yeah. So why did you decide for the double binder instead of the polarities? So is there a technical reason for that that makes life easier?
So I think the concept is very similar, that you distinguish carefully between the two endpoints of a channel. I think using the double binder is a bit simpler technically, because otherwise you get into questions like, okay, you've got x, you've got x plus, you've got x minus. So what is the exact relationship between x and x plus, if any? And you end up substituting. When you've got a bound variable on an input, say you write it without a polarity, and then you're substituting a polarized variable for an unpolarized variable, and it's all. I think now everything is simpler if you just use plain names with a double binder, rather than the plus and minus.
Are you going to start volume 2? Type behavioral equivalencies, for instance.
Well, it's possible that we would not be the best person to write that one either. Yeah, we're
Mine is a quick question. Do all proofs come mechanized?
No. In fact, you said, do they all come mechanized? Well, it's even worse than that. None of them are.
So a very quick question. What is the intended audience of the book, right? So is it us? Is it people outside? Is it undergraduates who are very motivated?
That's a good question. So your new PhD students, or maybe master students, if people are teaching courses at that level, or maybe other researchers from outside the field who want to find out more about it.
Okay.
That's the hope. How many of these people there are in the world, I don't know.
Thanks, Simon, again.
Thank you.